Hello, and welcome to Chapter 4, Section 2. Today we talk about experiments and how to set them up, how to design them, what we need to make a good experiment. So first, I want to talk a little bit about the difference between experiments and observational studies. We've talked about this before, but I just wanted to make sure and go into a little bit more detail with it. With observational studies, we're gathering data without influencing the individuals. We're only allowed to observe them, no sort of like messing with them or changing anything about their situation, their environment. But then in an experiment, that's exactly where we want to start changing those things. So we're going to impose some sort of change to it. Maybe they're called treatments. So we change something so that we can observe their behavior after those changes. The things that we're researching are called experimental units. So that could be people, that could be objects, could be animals, whatever you're trying to research. If the experimental units are people, we also sometimes call them subjects. But we're going to impose these changes and then we can measure their responses. So because we're imposing these changes and trying to control the environment for them, with experiments, we can also show causation now between the explanatory variable and the response variable. So that's something that we kind of touched on before when we talked about correlation, where you just had some sort of pattern or trend. When we looked at last chapter, the correlation between two variables. But if you have an actual well-designed experiment, you can actually show that one variable causes the other. And it has to be a well-designed experiment. So that's why in this section today, we want to talk about how to set up that well-designed experiment. So when we talk about a well-designed experiment, we need to have four main principles of this experimental design. The first one is called comparison. So with comparison, all we want to do is make sure that our experiment has some sort of design to it that compares two or more treatments, which makes sense. If you are only looking at one thing, like if, let's say we're testing out a vitamin or whatever, and we're trying to see if this vitamin makes you healthier, I don't know, being real vague here. But if you only give like this vitamin to one group of people and then you don't have anything else to compare that with, how would that even make sense? That's not an experiment. So we want to make sure we have two or more treatments. That way we can actually use them to compare. The next thing that we need in a well-designed experiment is random assignment. So after we have our multiple treatments, we want to make sure that we're randomly assigning our experimental units into these groups to have the different treatments. So you want to use some sort of random process. And last section when we talked about the different sampling methods, that's usually where this goes into play. So either like pick names out of a hat or roll dice to see which group you end up in. Somehow that assignment into treatments has to be a random process. Your goal when you do this is to make your groups as similar in their randomness as possible. You obviously don't want one group of your treatments all being the same, having some sort of similarity. Like if they're all male and then you have another group that's all female getting two different treatments, there's no way you can compare them, because what if gender actually affects the results of whatever you're testing? So you have to make sure that these groups, they're going to be similar in their randomness, their differences. The third principle of experimental design is control. So basically you want to make sure that as many of the other variables that might affect your response variable would be kept the same for all your treatment groups. And even better would be if you actually had a control group. And so you probably heard about a control group before. It's where you have one group that gets no treatment. So you basically are trying to keep that group of people or objects as normal as possible, whatever like the least amount of treatment could be, so that all the other variables are the same for them. One way to have or set up a control group is by giving those people in the control group a placebo. So a placebo is basically a fake treatment. So if it's a drug of some sort, it could be a pill doesn't have any medicine in it. A lot of times you'll hear like sugar pill. It could be a fake injection where they don't actually inject you with the medicine or drug or whatever. So what this does is basically helps prevent the placebo effect. So the placebo effect is basically sometimes you're giving them a placebo to this control group or whatever, but they still end up getting better, meaning that it was actually probably all in their heads, even without the drug, that they could still get better from this. So as like a mental thing or whatever, their high hopes actually help them feel better. So this is called the placebo effect. We actually don't want this because then we can't actually tell if the drug is working or not, and that doesn't help our experiment. And along these lines with the placebo, a lot of experiments are single blind, meaning only the researcher knows which treatment the subjects are getting, so that the subjects themselves don't know whether they're getting a placebo or an actual treatment. We can also look at experiments that are double blind. So in a double blind experiment, both the subjects and the people measuring their responses don't know what treatment they've been given. Obviously somebody has to know. So like the main researcher, boss dude way up there knows who got what, but then like, you have your underlings working for you to like go out and actually measure the responses. Those people don't know which treatments. And then obviously the subjects don't know. So this helps because then the subject can't, have the placebo effect. That won't be affected to your data. And then the people measuring those responses, they won't be biased in any sort of way either because they don't even know what treatments were given. Finally, the last principle of experimental design is replication. So replication just means you want to have enough experimental units in each of your treatment groups so that you can, test enough people. But then more importantly, you want to be able to see that the effects of the treatments within each of the treatment groups can actually be distinguishable instead of just having any differences by chance. So basically, we want to make sure that our results are statistically significant. Whatever data that we gather, whatever conclusions that we make, we want them to be statistically significant because, we're in a statistics class. And so we want to actually, when we look at the differences between each of the groups, we want to make sure those differences are large enough to actually occur not by chance. Because obviously, we might have differences between the treatment groups because of that random assignment, but we want to make sure that the differences between groups are large enough so that we can tell it's not just because there was like some random assignment difference there. This means that your treatments actually resulted in some sort of change to the response variable. Okay, so now let's get into the actual design aspect of our experiments. For our experimental designs, we have three different designs that we want to focus on. The first one is called the completely randomized design. In this design, all your experimental units are assigned to a treatment by chance, so some kind of chance process. And we want to be able to accurately explain what this chance process is for how to assign them to the different treatments. All right, so for example, let's say a scientist came up with a new vaccine that heals you from the coronavirus. Yay! Okay, so obviously we need to test this out because we need to make sure it works. We need to see how effective it actually is. So researchers are going to use an experiment to measure the effectiveness of this new vaccine. So they're going to set up 3 treatments, a placebo injection for our control group, a half-dose injection, and then a full-dose injection to see if we can actually tell the difference between the amount of the meds that you're going to get. We're also going to pretend we just have 50 people that we can experiment on. And so last time we talked about how to actually gather these people to be in your study. So we might have used some sort of sampling method to get these 50 people. So in order to randomly assign our 50 people into our 3 treatment groups, we need to use some sort of random process. There's lots of ways you can do this, so I'm just going to list a few. So one way is to use a die, because when you roll a die it's pretty random. You would need to state what each of the numbers that you land on could stand for. So let's say you roll a 1, we could say that means you're going into the control group, the placebo injection. If you roll a 2, that means you're going into the half-dose injection. If you roll a 3, you're going into the full dose injection. We could ignore all rolls of 4 to 6. They would just have to re-roll, something like that. So in this scenario, we made sure that each of the subjects getting assigned into a treatment group, they have an equal chance of getting into each one, because if we're only rolling between numbers 1 through 3, then they have an equal chance between each. We can also do this using a random number generator. So we would just say assign numbers 1, 2, and 3 to be each of the treatments, and then each person you would give them a random number. That's the treatment group they would go into. We could even use the random number table like we talked about last time. So if we're doing something like that, we would need to make sure that whatever numbers we look at, again, have that same chance of being chosen. So I could say, look at 1 digit at a time. 1 would stand for the placebo injection, 2 would stand for the half dose, and so on. But then we would need to make sure we state that we ignore digits 4 through 9 and 0, because 0 is also a digit. So these are all examples of ways you can randomly assign your subjects into treatments. If you only had 2 treatments, you could just flip a coin. That would also count as a random process. Let's say you had 10 treatments. Technically, on the AP test and whatever, on tests and things, you can actually say use like a 10-sided die. I'm sure they exist, those of you who play Dungeons and Dragons. But yeah, so as long as your process that you're explaining is random, is a sort of random process, then you're good to go. And because I'm setting up this experiment, I also want to explain what do I do once I have my treatment group set up. So after I give them all the injection, I want to make sure that I go and measure the proportion of subjects who recover from the coronavirus, because that's how I'm going to see the results, right? So we will always want to say what we're measuring, and then at the very end, we're going to compare the results between treatment groups. So these are all things that you want to mention. You want to have that random assignment, you want to measure and then state for that problem what you're measuring, and then at the very end, compare your results, state like what you're comparing, and amongst 2. Another kind of experimental design is called the randomized block design. So this one's a little bit more specific because it actually controls a variable that you already know is going to affect your data. So I'm going to use the same example as before. We have this new vaccine for the coronavirus, but I'm thinking gender might play a role in the effectiveness of the vaccine. So I want to already set up my experiments so that I account for that. So I'm actually going to separate genders into groups so that I have blocks. So within this block design, each of the groups are called blocks. So I'm going to have one block that's all males, one block that's all females, and then I'm going to test each of the treatment groups or each of the blocks separately. So it's like running separate experiments here. So with my male block, I'm going to give them the 3 treatments that way, and then I just compare amongst the males. With the females, I'm also going to give the 3 treatment groups to them and randomly assigned as well to the different treatment groups, but then at the very end, I'm going to measure and compare just amongst the females. So that way, I already know that I expect to see differences between the genders, so that at the very end, let's say that the gender actually affects it, then I should be able to see differences in the proportions amongst the males and the females. And that's something that's clear to see, versus if I hadn't done the blocking to begin with and I had just done a completely randomized design like we talked about before with the completely randomized design, my treatment groups would be a mix of both male and female already. So I wouldn't be able to tell if gender played a role in that. And I wouldn't be able to tell if there were just small differences. I can't tell that it's statistically significant because I don't know whether the gender actually helped create those differences or not. So if I were to write this out in an explanation of how I would set this up, I would say something about splitting the 50 people into blocks by gender. Then I'm going to randomly assign the 3 treatments to all the males, all the females, measure the proportion of subjects who recover from the males, and then compare the results between the treatment groups of just the males. Do the same thing with the females. And you can always just say like similarly with the females instead of rewriting that whole part. And then lastly, you also want to compare the results between the 2 blocks that you had, so the males and the females. And obviously you would, when it says randomly assigned, you would need to explain your process for the random assignment as well. And finally, the last type of design that I want to talk about is the matched pairs design. Matched pairs is very specific. You can only do this design when you only have 2 treatments. So if you have any more than that, then you can't use the matched pairs design. And so the way matched pairs design works is with your 2 treatments, either you have a pair of subjects that are super similar to each other, or just an individual who's going to receive both treatments. So if it's just an individual, like one person receiving both treatments, the order of the treatments that they receive would be randomized. And that's how you would get that random assignment that we need within each experiment. A lot of times this matched pairs design is used for like before and after type studies. Or you might also see 2 very similar subjects being paired, and then the 2 treatments are given to those 2 people, again, randomly assigned. And then they would just compare results with each other because they are so similar. And so the reason why we like to use the individual is because that individual is already very similar to themselves. So it's easy to compare that way. If you've ever heard of any experiments done on twins, it's usually in the matched pairs design because twins are obviously very similar to each other genetically, and so that's when they can each be given one of the 2 treatments and then measured and compared that way. Alright, so that's all the designs that I want to talk about. Thank you for watching. Have a great day. Bye.